know them. We know when we have toothache, when we feel thirsty, what we were dreaming when we woke up, and so on. Dr. Watson might say that the dentist can't know we have toothache by observing a cavity in a tooth. I will not reply that the dentist is often mistaken. This may be merely because the art of dentistry has not been sufficiently perfected. I will concede as possible, in the future, a state of odontology in which the dentist would always know whether I'm feeling toothache. But even then, his knowledge has a different character from mine. His knowledge is an inference, based upon the inducive law that people with such and such cavities suffer pain of a certain kind. But this law cannot be established by observation of cavities alone. It requires that, where these are observed, the people who have them should tell us that they feel toothache, and more than that, they must be speaking the truth. Purely external observation can discover that people with cavities say they have toothache, but not that they haven't. Saying one has toothache is a different thing from having it, and if not, we could cure toothache by not talking about it, and so save our dentist's bills. I am sure the expert opinion of dentists will agree with me that this is impossible. To this argument, however, it might be replied that having toothache is a state of the body, and knowing I have toothache is a response to this bodily stimulus. It will be said that, theoretically, the state of my body when I have toothache can be observed by an outsider, who can then also know that I have toothache. This answer, however, does not really meet the point. When the outside observer knows that I have toothache, not only is his knowledge based upon an inductive inference, as we've already seen, but his knowledge of the inferred term, toothache, must be based upon personal experience. No knowledge of dentistry could enable a man to know what toothache is if he had never felt it. If, then, toothache is really a state of the body, which at the moment I neither affirm nor deny, it is a state of the body which only the man himself can perceive. In a word, whoever has experienced toothache and can remember it has knowledge that cannot be possessed by a man who has never experienced toothache. Take next our knowledge of our own dreams. Dr. Watson has not, so far as I know, ever discussed dreams, but I imagine he would say something like this. In dreams, there are probably small laryngeal movements, such as, if they were greater, would lead to speech. Indeed, people do sometimes cry out in dreams. There may also be stimulations of the sense organs, which produce unusual reactions owing to the peculiar physiological condition of the brain during sleep. But all these reactions must consist of small movements, which could theoretically be seen from outside, say by some elaboration of X-ray apparatus. This is all very well, but it is hypothetical, and the dreamer himself knows his dreams without all this elaborate inference. Can we say that he really knows these hypothetical small bodily movements, although he thinks he knows something else? Presumably in Dr. Watson's position, and it must be admitted that with a definition of knowledge such as we considered in Chapter 8, such a view is not to be dismissed offhand as obviously impossible. Moreover, if we are to say that perception gives knowledge of the physical world, we shall have to admit that what we are perceiving might be quite different from what it seems to be. A table does not look like a vast number of electrons and protons, nor like trains of waves moving and clashing. Yet this is the sort of thing a table is said to be by modern physicists. If then, what seems to us to be just a table, such as may be seen any day, is really this odd sort of thing, it is possible that what seems to us to be a dream is really a number of movements in the brain. This again is all very well, but there is one point which it fails to explain, namely, what is meant by seeing. A dream or a table seems to be one sort of thing, while it is really another. We shall have to admit that it really seems, and that what it seems to be has a reality. We only arrive at what it really is by an inference, valid or unvalid, from what it seems to be. If we are wrong about the seeming, we must be doubly wrong about the reality. since the sole ground for asserting the table composed of electrons and protons is the table that we see, i.e. the C table. We must therefore treat C with respect. Let us consider Dr. Watson watching a rat in a maze. He means to be quite objective and report only what really goes on. Can he succeed? In what sense he can. He can use words about what he sees, which are the same as any other scientifically trained observer would use if he watches the same rat at the same time. But Dr. Watson's objectivity emphatically does not consist in using the same words as other people use. His vocabulary is very different from that of most psychologists. He cannot take as the sole test of truth the consensus of mankind. Securus judicat orbis terrarum is another example of a Latin tag which is false, and which certainly Dr. Watson would not consider true. It has happened again and again in human history that a man who said something that had never been said before turned out to be right, while the people who repeated the wise saws of their forefathers were talking nonsense. Therefore, when Dr. Watson endeavors to eliminate subjectivity in observing rats, he does not mean that he says what everybody else says. He means that he refrains from inferring anything about the rat beyond its bodily movements. This is all to the good, but I think he fails to realize that almost as long and difficult an inference is required to give us knowledge of the rat's bodily movements as to give us knowledge of its mind. And what is more, the data from which we must start in order to get to know the rat's bodily movements are data of just the sort that Dr. Watson wishes to avoid, namely, private data patent to self-observation, but not patent to anyone except the observer. This is the point at which, in my opinion, behaviorism as a final philosophy breaks down. When several people simultaneously watch a rat in a maze, or any other example of what we should naturally regard as matter in motion, there is by no means complete identity between the physical events which happen at the surface of their eyes and constitute the stimuli to their perceptions. There are differences of perspective, of light and shade, of apparent size, and so on, all of which will be reproduced in photographs taken from the places where the eyes of the several observers are. These differences produce differences in the reactions of the observers, differences which a quite unlooking person may overlook, but which are familiar to every artist. Now, it is contrary to all scientific canons to suppose that the object perceived, in addition to affecting us in the way of stimulus and reaction, also affects us directly by some mystical epiphany. Certainly it is not what any behaviorists would care to assert. Our knowledge of the physical world, therefore, must be contained in our reaction to the stimulus which reaches us across the intervening medium. And it seems hardly possible that our reaction should have a more intimate relation to the object than the stimulus has. Since the stimulus differs for different observers, the reaction also differs. Consequently, in all our perceptions of physical processes, there is an element of subjectivity. If, therefore, physics is true in its broad outlines, as the above argument supposes, what we call perceiving a physical process is something private and subjective, at least in part, and is yet the only possible starting point for our knowledge of the physical world. There is an objection to the above argument which might naturally be made, but it would be, in fact, it may be said that we do not, in fact, proceed to infer the physical world from our perceptions, but that we begin at once with a rough and ready knowledge of the physical world, and only at a late stage of sophistication compel ourselves to regard our knowledge of the physical world as an inference. What is valid in this statement is the fact that our knowledge of the physical world is not at first inferential, but that is only because we take our percept to be the physical world. Sophistication and philosophy come in at a stage at which we realize that the physical world cannot be identified with our percepts. When my boy was 3 years old, I showed him Jupiter, and told him that Jupiter was larger than the Earth. He insisted that I must be speaking of some other Jupiter, because, as he patiently explained, the one he was seeing was obviously quite small. After some efforts, I had to give it up and leave him unconvinced. In the case of the heavenly bodies, adults have got used to the idea that what is really there can only be inferred from what they see. But where rats in mazes are concerned, they still tend to think that they are seeing what is happening in the physical world. The difference, however, is only one of degree, and naive realism is untenable in the one case as in the other. There are differences in the perceptions of two persons observing the same process. There are sometimes indiscoverable differences between two perceptions of the same person observing different processes, e.g., pure water and water full of bacilli. The subjectivity of our perceptions is thus of practical as well as theoretical importance. I am not maintaining that what we primarily know is our own perceptions. This is largely a verbal question, but with the definition of knowledge given in Chapter 8, it will be correct to say that from the first we know external objects, the question is not as to what are the objects we know, but rather as to how accurately we know them. Our non-inferential knowledge of an object cannot be more accurate than our reaction to it, since it is part of that reaction, and our reaction cannot be more accurate than the stimulus. But what on earth can you mean by the accuracy of a stimulus, I may be asked? I mean just the same as by the accuracy of a map or a set of statistics. I mean a certain kind of correspondence. One pattern is an accurate representation of another if every element of the one can be taken as the representative of just one element of the other, and the relations that make the one set into a pattern correspond with relations making the other set into a pattern. In this sense, writing can represent speech with a certain degree of accuracy. To every spoken word, a written word corresponds, and to the time order of the spoken words, the space order of the written words corresponds. But there are inflections and tones of voice that cannot be represented in writing, except to some extent by musical notation. A gramophone record is a much more accurate representation of vocal sounds than any writing can be. But even the best gramophone record fails to be completely accurate. The impression made upon an observer is very analogous to a gramophone record or a photograph, but usually less accurate, owing to the influence of the law of association and the lack of delicacy in our senses. And whatever limitations there are to the accuracy of our impressions are limitations to the accuracy of our non-inferential knowledge of the external world. Another point. If we accept the definition of knowledge given in Chapter 8, which was framed so far as to be favorable as possible to behaviorism, a given reaction may be regarded as knowledge of various different occurrences. When we see Jupiter, we have, according to the definition, knowledge of Jupiter. But we also have knowledge of the stimulus at the surface of the eye, and even of the process in the optic nerve. For it is arbitrary at what point we start in the process leading to a certain event in the brain. This event and the consequent bodily action may be regarded as a reaction to a process starting at any earlier point. And the nearer our starting point is to the brain, the more accurate becomes the knowledge displayed in our reaction. A lamp at the top of a tall building might produce the same visual stimulus as Jupiter, or at any rate, one practically indistinguishable from that produced by Jupiter. A blow on the nose might make us see stars. Theoretically, it should be possible to apply a stimulus direct to the optic nerve, which should give us a visual sensation. Thus, when we think we see Jupiter, we may be mistaken. We are less likely to be mistaken if we say that the surface of the eye is becoming stimulated in a certain way, and still less likely to be mistaken if we say that the optic nerve is being stimulated in a certain way. We do not eliminate the risk of error completely unless we confine ourselves to saying that an event of a certain sort is happening in the brain. This statement may still be true if we see Jupiter in a dream. But, I shall be asked, what do you know about what is happening in the brain? Clearly nothing. Not so, I replied. I know about what is happening in the brain exactly what naive realism thinks it knows about what is happening in the outside world. But this needs explaining, and there are other matters that must be explained first. When the light from a fixed star reaches me, I see the star if it is night and I am looking in the right direction. The light started years ago, probably many years ago, but my reaction is primarily to something that is happening now. When my eyes are open, I see the star. When they are shut, I do not. Children discover at a fairly early age that they see nothing when their eyes are shut. They are aware of the difference between seeing and not seeing, and also of the difference between eyes open and eyes shut. Gradually, they discover that these two differences are correlated. I mean that they have expectations of which this is the intellectualist transcription. Again, children learn to name the colors and to state correctly whether a thing is blue or red or yellow or whatnot. They ought not to be sure that light of the appropriate wavelength started from the object. The sun looks red in a London fog. Grass looks blue through blue spectacles. Everything looks yellow to a person suffering from jaundice. But suppose you ask, what color are you seeing? The person who answers in these cases, red for the sun, blue for the grass, and yellow for the sick room of the jaundiced patient, is answering quite truly. And in each of these cases, he is stating something that he knows. What he knows in such cases is what I call a percept. I shall contend later that from the standpoint of physics, a percept is in the brain. For the present, I am only concerned to say that a percept is what is most indubitable in our knowledge of the world. To behaviorism as a metaphysic, one may put the following dilemma. Either physics is valid in its main lines, or it is not. If it is not, we know nothing about the movements of matter. For physics is the result of the most serious and careful study of which the human intelligence has hitherto been capable. If, on the other hand, physics is valid in its main lines, any physical process starting either inside or outside the body will, if it reaches the brain, be different if the intervening medium is different. Moreover, two persons, initially very different, may become indistinguishable as they spread and grow fainter. On both grounds, whatever happens in the brain is not connected quite accurately with what happens elsewhere, and our perceptions are therefore infected with subjectivity on purely physical grounds. Even, therefore, when we assume the truth of physics, what we know most indubitably through perception is not the movements of matter, but certain events in ourselves which are connected in a manner not quite variable with the movements of matter. To be specific, when Dr. Watson watches rats in mazes, what he knows, apart from difficult inferences, are certain events in himself. The behavior of the rats can only be inferred by the help of physics, and is by no means to be accepted as something accurately knowable by direct observation. I do not, in fact, entertain any doubts that physics is true in its main lines. The interpretation of physical formulae is a matter as to which a considerable degree of uncertainty is possible, but we cannot well doubt that there is an interpretation which is true roughly and in the main. I shall come to the question of interpretation later. For the present, I shall assume that we may accept physics in its broad outlines, without troubling to consider how it is to be interpreted. On this basis, the above remarks on perception seem undeniable. We are often misled as to what is happening, either by peculiarities of the medium between the object and our bodies, or by unusual states of our bodies, or by a temporary or permanent abnormality in the brain. But in all these cases, something is really happening, as to which, if we turn our attention to it, we can obtain knowledge that is not misleading. At one time, when, owing to illness, I had been taking a great deal of quinine, I became hypersensitive to noise, so that when the nurse rustled the newspaper, I thought she was smelling a scuttle of coals on the floor. The interpretation was mistaken, but it was quite true that I heard a loud noise. It is a commonplace that a man whose leg has been amputated can still feel pains in it. Here again, he does really feel the pains, and is only mistaken in his belief that they come from his leg. A percept is an observable event, but its interpretation as knowledge of this or that event in the physical world is liable to be mistaken, for reasons which physics and physiology can make fairly clear. The subjectivity of percepts is a matter of degree. They are more subjective when people are drunk or asleep than when they are sober and awake. They are more subjective in regard to distant objects than in regard to such as are near. They may acquire various peculiar kinds of subjectivity through injuries to the brain or to the nerves. When I speak of a percept as subjective, I mean that the physiological inferences to which it gives rise are mistaken or vague. This is always the case to some extent, but much more so in some circumstances than in others, and the sort of defect that leads to mistakes must be distinguished from the sort that leads to vagueness. If you see a man a quarter of a mile away, you can see that it is a man if you have normal eyesight, but you probably cannot tell who it is, even if, in fact, it is someone you know. This is vagueness in the percept. Inferences you draw correctly so far as they go, but they do not go very far. On the other hand, if you are seeing double and think there are two men, you have a case of mistake. Vagueness, to a greater or less extent, is universal and inevitable. Mistakes, on the other hand, can usually be avoided by taking trouble and by not always trusting to physiological inference. Anyone can see double on purpose by focusing on a distant object and noticing a near one. But this will not cause mistakes, since the man is aware of the subjective element in his double vision. Similarly, we are not deceived by after images, and only dogs are deceived by gramophones. From what has been said in this chapter, it is clear that our knowledge of the physical world, if it is to be made as reliable as possible, must start from percepts, and must scrutinize the physiological inferences by which percepts are accompanied. Physiological inference is inference in the sense that it sometimes leads to error, and physics gives reason to expect that percepts will, in certain circumstances, be more or less deceptive if taken as signs of something outside the brain. It is these facts that give a subjective cast to the philosophy of physics, made in its beginnings. We cannot start cheerfully with a world of matter in motion, as to which any two sane and sober observers must agree. To some extent, each man dreams his own dream, and the disentangling of the dream element in our percepts is no easy matter. This is, indeed, the work that scientific physics undertakes to do. End of chapter 12. Chapter 13 of Philosophy by Bertrand Russell. The Sleeper Fox recording is in the public domain. Physical and perceptual space. Perhaps there is nothing so difficult for the imagination as to teach it to feel about space as modern science compels us to think. This is the task which must be attempted in the present chapter. We said in chapter 12 that we know about what is happening in the brain exactly what naive realism thinks it knows about what is happening in the world. This remark may seem cryptic. It must now be expanded and expounded. The gist of the matter is that percepts, which we spoke about at the end of last chapter, are in our heads. That percepts are what we can know with most certainty, and that percepts contain what naive realism thinks it knows about the world. But when I say that my percepts are in my head, I am saying something which is ambiguous until the different kinds of space have been explained, for the statement is only true in connection with physical space. There is also a space in our percepts, and in this space the statement would not be true. When I say that there is space in our percepts, I mean nothing at all difficult to understand. I mean to take the sense of sight, which is the most important in this connection, that in what we see at one time, there is up and down, right and left, inside and outside. If we see, say, a circle on a blackboard, all these relations exist within what we see. The circle has a top half and a bottom half, a right-hand half and a left-hand half, an inside and an outside. Those relations alone are enough to make up a space of sorts. But the space of everyday life is filled out with what we derive from touch and movement, how a thing feels when we touch it, and what movements are necessary in order to grasp it. Other elements also come into the genesis of the space in which everybody believes who has not been troubled by philosophy. But it is unnecessary, for our purposes, to go into this question any more deeply. The point that concerns us is that a man's percepts are private to himself. What I see, no one else sees. What I hear, no one else hears. What I touch, no one else touches, and so on. True, others hear and see something very like what I hear and see, if they are suitably placed, but there are always differences. Sounds are less loud at a distance. Objects change their visual appearance according to the laws of perspective. Therefore, it is impossible for two persons at the same time to have exactly identical percepts. It follows that the space of percepts, like the percepts, must be private. There are as many perceptual spaces as there are percipients. My percept of a table is outside my percept of my head, in my perceptual space. But it does not follow that it is outside my head as a physical object in physical space. Physical space is neutral and public. In this space, all my percepts are in my head, even the most distant star, as I see it. Physical and perceptual space have relations, but they are not identical, and failure to grasp the difference between them is a potent source of confusion. To say that you see a star when you see the light that come from it is no more correct than to say that you see New Zealand when you see a New Zealander in London. Your perception when, as we say, you see a star is causally connected, in the first instance, with what happens in the brain, the optic nerve, and the eye. Then, with a light wave which, according to physics, can be traced back to the star as its source. Your sensations will be closely similar if the light comes from a lamp at the top of a mast. The physical space in which you believe the real star to be is an elaborate inference. What is given is the private space in which the speck of light you see is situated. It is still an open question whether the space of sight has depth or is merely a surface, as Berkeley contended. This does not matter for our purposes. Even if we admit that sight alone shows a difference between an object a few inches from the eyes and an object several feet distant, yet you certainly cannot, by sight alone, see that a cloud is less distant than a fixed star, though you may infer that it is because it can hide the star. The world of astronomy, from the point of view of sight, is a surface. If you were put in a dark room with little holes cut in the ceiling and the pattern of the stars letting light come through, there would be nothing in your immediate visual data to show that you were not seeing the stars. This illustrates what I mean by saying that what you see is not out there in the sense of physics. We learn in infancy that we can sometimes touch objects we see and sometimes not. When we cannot touch them at once, we can sometimes do so by walking to them. That is to say, we learn to correlate sensations of sight with sensations of touch, and sometimes with sensations of movement, followed by sensations of touch. In this way, we locate our sensations in a three-dimensional world. Those which involve sight alone we think of as external, but there is no justification for this view. What you see when you see a star is just as internal as what you feel when you feel a headache. That is to say, it is internal from the standpoint of physical space. It is distant in your private space because it is not associated with sensations of touch, and cannot be associated with them by means of any journey you can perform. Your own body, as known to you through direct experience, is quite different from your own body as considered in physics. You know more about your own body than about any other through direct experience, because your own body can give you a number of sensations that no other body can. For instance, all kinds of bodily pains. But you still know it is only through sensations. Apart from inference, it is a bundle of sensations, and therefore quite different prima facie from what physics calls a body. Most of the things you see are outside what you see when, as one says, you see your own body. That is to say, you see certain other patches of color differently situated in visual space, and say you are seeing things outside your body. But from the point of view of physics, all that you see must count as inside your body. What goes on elsewhere can only be inferred. Thus, the whole space of your sensible world with all its percepts counts as one tiny region from the point of view of physics. There is no direct spatial relation between what one person sees and what another sees, because no two ever see exactly the same object. Each person carries about a private space of his own, which can be located in physical space by indirect methods, but which contains no place in common with another person's private space. This shows how entirely physical space is a matter of inference and construction. To make the matter definite, let us suppose that a physiologist is observing a living brain, no longer an impossible supposition as it would have been formerly. It is natural to suppose that what the physiologist sees is in the brain he is observing, but if we are speaking of physical space, what the physiologist sees is in his own brain. It is in no sense in the brain that he is observing, though it is in the percept of that brain, which occupies part of the physiologist's perceptual space. Causal continuity makes the matter perfectly evident. Light waves travel from the brain that is being observed to the eye of the physiologist, at which they only arrive after an interval of time, which is finite, though short. The physiologist sees what he is observing only after the light waves have reached his eye. Therefore, the event which constitutes his seeing comes at the end of a series of events which travel from the observed brain into the brain of the physiologist. We cannot, without a preposterous kind of discontinuity, suppose that the physiologist's percept, which comes at the end of this series, is anywhere else but in the physiologist's head. This question is very important and must be understood if metaphysics is ever to be got straight. The traditional dualism of mind and matter, which I regard as mistaken, is intimately connected with confusions on this point. So long as we adhere to the conventional notions of mind and matter, we are condemned to a view of perception which is miraculous. We suppose that a physical process starts from a visible object, travels to the eye, there changes into another physical process, causes yet another physical process in the optic nerve, finally produces some effect in the brain, simultaneously with which we see the object from which the process started, the seeing being something mental, totally different in character from the physical processes which precede and accompany it. This view is so queer that metaphysicians have invented all sorts of theories designed to substitute something less incredible, but nobody noticed an elementary confusion. To return to the physiologist observing another man's brain, what the physiologist sees is by no means identical with what happens in the brain he is observing, but is a somewhat remote effect. From what he sees, therefore, he cannot judge whether what is happening in the brain he is observing is or is not the sort of event that he would call mental. When he says that certain physical events in the brain are accompanied by mental events, he is thinking of physical events as if they were what he sees. He does not see a mental event in the brain he is observing, and therefore supposes there is, in that brain, a physical process which he can observe, and a mental process which he cannot. This is a complete mistake. In the strict sense, He cannot observe anything in the other brain, but only the percepts which he himself has when he is suitably related to that brain, eye to microscope, etc. We first identify physical processes with our percepts, and then, since our percepts are not other people's thoughts, we argue that the physical processes in their brains do something quite different from their thoughts. In fact, everything that we can directly observe of the physical world happens inside our heads and consists of mental events in at least one sense of the word mental. It also consists of events which form part of the physical world. The development of this point of view will lead us to the conclusion that the distinction between mind and matter is illusory. The stuff of the world may be called physical or mental or both or neither, as we please. In fact, the words serve no purpose. There is only one definition of the words that is unobjectionable. Physical is what is dealt with by physics, and mental is what is dealt with by psychology. When, accordingly, I speak of physical space, I mean the space that occurs in physics. It is extraordinarily difficult to divest ourselves of the belief that the physical world is the world we perceive by sight and touch, even if, in our philosophic moments, we are aware that this is an error, and nevertheless fall into it again as soon as we are off our guard. The notion that what we see is out there in physical space is one which cannot survive when we are grasping the difference between what physics supposes to be really happening and what our senses show us is happening. But it is sure to return and plague us when we begin to forget the argument. Only long reflection can make a radically new point of view familiar and easy. Our illustrations hitherto have been taken from the sense of sight. Let us now take one from the sense of touch. Suppose that, with your eyes shut, you let your fingertip press against a hard table. What is really happening? The physicist says that your fingertip and the table consist, roughly speaking, of vast numbers of electrons and protons. More correctly, each electron and proton is to be thought of as a collection of processes of radiation. But we can ignore this for our present purposes. Although you think you are touching the table, no electron or proton in your finger ever really touches an electron or proton in the table, because this would develop an infinite force. When you press, repulsions are set up between parts of your finger and parts of the table. If you try to press upon a liquid or a gas, there is room in it for the parts that are repelled to get away. But if you press a hard solid, the electrons and protons that try to get away, because electrical forces from your finger repel them, are unable to do so, because they are crowded close to others, which elbow them back to more or less their original position, like people in a dense crowd. Therefore, the more you press, the more they repel your finger. The repulsion consists of electrical forces, which set up in the nerves a current whose nature is not very definitely known. This current runs into the brain, and there has effects which, so far as the physiologist is concerned, are almost wholly conjectural. But there is one effect which is not conjectural, and that is the sensation of touch. This effect, owing to physiological inference, or perhaps to a reflex, is associated by us with the fingertip. But the sensation is the same if, by artificial means, the parts of the nerve nearer the brain are suitably stimulated, e.g., if your hand has been amputated and the right nerves are skillfully manipulated. Thus, our confidence that touch affords evidence of the existence of bodies at the place which we think is being touched is quite misplaced. As a rule, we are right, but we can be wrong. There is nothing of the nature of an infallible revelation about the matter. And even in the most favorable case, the perception of touch is something very different from the mad dance of electrons and protons trying to jazz out of each other's way, which is what physics maintains is really taking place at your fingertip, or at least it seems very different. But as we shall see, the knowledge we derive from physics is so abstract that we are not warranted in saying that what goes on in the physical world is, or is not, intrinsically very different from the events that we know through our own experiences. End of chapter 13. Chapter 14, Philosophy by Bertrand Russell. This LibriVox recording is in the public domain. Perception and Physical Causal Laws. In an earlier chapter, we saw the inadequacy of the traditional notion of cause, without adequately explaining the causal laws which are a substitute for the practice of science. The time has now come when it is possible to remedy this defect, and in so doing, to fit perception into its place in the chain of physical causation and recapitulate the main points of previous arguments. The old view was that an event A will always be followed by a certain event B, and that the problem of discovering causal laws is the problem, given an event B, of finding that event A, which is its invariable antecedent, or vice versa. At an early stage of the science, this point of view is useful. It gives laws which are true usually, though probably not always, and it affords the basis for more exact laws. But it has no philosophical validity, and is superseded in science as soon as we arrive at genuine laws. Genuine laws in advanced sciences are practically always quantitative laws of tendency. I will try to illustrate by taking the simplest possible case in physics. Imagine a hydrogen atom in which the electron is revolving not in the minimum orbit, but in the next, which has 4 times the minimum radius. So long as this state continues, the atom has no external effects, apart from its infinitesimal gravitational action. We cannot, therefore, obtain any evidence of its existence except when it changes its state. In fact, our knowledge of atoms is like that which a ticket collector has of the population of his town. He knows nothing of those who stay quietly at home. Now, at some moment, according to the laws of which we have only statistical knowledge, the electron in our atom jumps to a smaller orbit, and the energy lost to the atom travels outward in a light wave. We know no causal law as to when the electron will jump, though we know how far it will jump, and exactly what will happen in the neighborhood when it does. At least, when I say we know exactly what will happen, I ought to say that we know exactly the mathematical laws of what will happen. A series of events, having quantitative characteristics which obey certain equations, will travel outward in all directions from the electron, and will proceed quite regularly, like ripples on a pool, until other matter is encountered. We have here one important and apparently fundamental kind of causal law, the kind regulating the propagation of light in vacuum. This is summed up in Maxwell's equations, which enable us to calculate the diffusion of an electromagnetic disturbance starting from a source. So long as 2 such disturbances do not meet, the matter is exceedingly simple, but the equations also tell us what happens when they do meet. We then have, as always in traditional physics, 2 separate tendencies, which have a resultant compounded according to mathematical laws, of which the parallelogram law is the oldest and simplest. That is to say, each previous circumstance in the space-time neighborhood contributes a tendency, and the resulting event is obtained by compounding these tendencies according to a mathematical law. So far, we have been considering only electromagnetic phenomena in empty space. We have another set of facts about empty space, namely those upon which gravitation depends. These have to do with the structure of space-time, and show that this structure has singularities in the region where there is matter, which spread with diminishing intensity to get away from these regions. You may conceive the structure of space-time on the analogy of a pond with a fountain playing in it, so that wherever a spray falls from the fountain, there is a little hill of water, which flattens quickly as you get away from the spot where the spray falls. Here again, the same sort of thing applies. To infer the structure in a small region of space-time from that in the neighborhood, it will be necessary to superpose a number of tendencies according to mathematical rules. Thus, philosophically, this introduces no novelty. But now consider what happens when the wave of light, which started from our hydrogen atom, comes in contact with matter. Various things may happen. The matter may absorb all or some of the energy of the light ray. This is the interesting case from our point of view. The absorption may take the form of causing the electrons to move in larger orbits, in which case, later, when they return to their previous orbits, we get the phenomenon of fluorescence. Or the body may become heated, or it may visibly move, like a radiometer. The effects upon bodies depend upon the bodies as well as the light. Some of them can be individually predicted. Others can only be calculated in statistical averages. This depends upon whether quantum considerations come into mind. Where they do, we can enumerate possibilities and state the relative frequencies with which they will be realized, but we cannot tell which will be realized in any given case. So far, we have considered the radiation of energy from matter into empty space, its propagation in empty space, and its impact on matter from empty space. We have not considered the history of a given piece of matter, or the distinction between matter and empty space. The essence of matter appears to be this. We can distinguish series of events in space-time which have a certain kind of close resemblance to each other, such that common sense regards them as manifestations of one thing. But when we look closely at the question, it turns out that what physics offers is something more abstract than this. Take, e.g., the continued existence of a certain electron. This means to say that events in a certain neighborhood will be such as can be calculated on the assumption that there is an electric charge of a certain standard magnitude in the middle of that neighborhood, and that the neighborhoods of which this is true form a tube in space-time. So long as we stick to the standpoint of pure physics, there is a certain air of taking in each other's washing about the whole business. Events in empty space are only known as regards their abstract mathematical characteristics. Matter is only an abstract mathematical characteristic of events in empty space. This seems rather a cold world, but as a matter of fact, we know some things that are a little more concrete. We know, e.g., what it feels like when we see things. From the point of view of physics, when our light wave starts out through empty space, if it presently reaches our eye, we know one link in the causal chain, namely the visual sensation, otherwise than as a term in an abstract mathematical formula. And it is this one term which forms the basis for our belief in all the rest. Seeing is believing. At this point, I propose to make a brief digression on the subject of our evidence for causal laws. The laws for which we first get evidence are such as do not hold always, but only as a general rule. As a rule, when you decide to move your arm, it moves, but sometimes it is paralyzed and remains motionless. As a rule, when you say, "How do you do?" to an old friend, he says the same to you. But he may have grown blind and deaf since you last saw him and not notice your words or gesture. As a rule, if you put a match to gunpowder, it explodes, but it may have got damp. It is such common but not invariable rules of sequence that we notice first. Science is always seeking to assess the resultant of a number of tendencies. We cannot know what the resultant will be unless we know a great deal about the neighborhood concerned. For example, I might, within the next few seconds, be hit on the head by a meteorite. To know whether this is going to happen, I must know what matter is to be found in the neighborhood of the Earth. This illustrates that actual predictions based upon laws which are perfectly valid may always be falsified by some unknown fact of what we may call geography. Moreover, we can never be sure that our scientific laws are quite right. Of this, the Einsteinian modification of the law of gravitation is afforded a notable instance. Let us now return to the relation between perception and the causal laws of physics. Having realized the abstractness of what physics has to say, we no longer have any difficulty in fitting the visual sensation into the causal series. It used to be thought mysterious that purely physical phenomena should end in something mental. This was because people thought they knew a lot about physical phenomena and were sure they differed in quality from mental phenomena. We now realize that we know nothing of the intrinsic quality of physical phenomena except when they happen to be sensations, and that therefore there is no reason to be surprised that some are sensations, or to suppose that the others are totally unlike sensations. The gap between mind and matter has been filled in, partly by new views of mind, but much more by the realization that physics tells us nothing as to the intrinsic character of matter. I conceive what happens when we see an object more or less on the following lines. For the sake of simplicity, let us take a small self-luminous object. In this object, a certain number of atoms are losing energy and radiating it according to the quantum principle. The resulting light waves become superposed according to the usual mathematical principles. Each part of each light wave consists of events in a certain region of space-time. On coming in contact with the human body, the energy in the light wave takes new forms, but there is still causal continuity. At last, it reaches the brain, and there one of its constituent events is what we call a visual sensation. This visual sensation is popularly called seeing the object from which the light waves started, or from which they were reflected if the object was not self-luminous. Thus, what is called a perception is only connected with its object through the laws of physics. Its relation to the object is causal and mathematical. We cannot say whether or not it resembles the object in any intrinsic respect, except that both it and the object are brief events in space-time. I think we may lay down the following universal characteristics of causal laws in an advanced science. Given any event, there are other events at neighboring places in space-time which will occur slightly later if no other factors intervene, but in practice, other factors almost always do intervene, and in that case, the event which actually occurs at any point in space-time is a mathematical resultant of those which would have followed the various neighboring events if they had been alone concerned. The equations of physics give the rules according to which events are connected, but all are of the above sort. Formerly, it was thought that the equations of physics sufficed, theoretically, to determine the course of affairs in the physical world, given all the facts about some finite stretch of time, however short. Now it appears that this is not the case, so far as the known equations are concerned. The known equations suffice to determine what happens in empty space, and statistical averages as to what happens to matter. But they do not tell us when an individual atom will absorb or radiate energy. Whether there are laws other than those of statistics governing the behavior of an individual atom in this respect, we do not know. It should be observed that there are causal laws of a different sort from those of pure physics. Such are the laws that light waves cause visual sensations and sound waves cause auditory sensations. All the empirical evidence for physics rests upon such laws. Therefore, nothing in physics can have a higher degree of certainty than such laws have. Let us stop a moment to ask what we mean by cause in this connection. The connection of light waves and visual sensation looks a little different according as we start with physics or with psychology, though, of course, ultimately the result must be the same. Let us first start with physics. I say then that when a light wave travels outwards from a body, there are successive events in successive places, and that the corresponding event in a brain behind a normal eye is a visual sensation. This is the only event in the whole series about which I can say anything not purely abstract and mathematical. Now, let us start from the sensation. This sensation is one of a vast series of connected events, traveling out from a center according to certain mathematical laws, in virtue of which the sensation enables me to know a good deal about events elsewhere. That is why the sensation is a source of physical knowledge. It will be seen that, according to the view I have been advocating, there is a difficulty about interaction between mind and body. The sensation is merely one link in a chain of physical causation. When we regard the sensation as the end of such a chain, we have what would be regarded as an effect of matter on mind, when as the beginning, an effect of mind on matter. But mind is merely a cross-section in the stream of physical causation, and there's nothing odd about its being both an effect and a cause in the physical world. Thus, physical causal laws are those that are fundamental. There seems no reason to regard causation as a priori, though this question is not simple. Given certain very general assumptions as to the structure of spacetime, there are bound to be what we have called causal laws. These general assumptions must really replace causality as our basic principles. But general as they are, they cannot be taken as a priority. They are the generalization and abstract epitome of the fact that there are causal laws. And this must remain merely an empirical fact, which is rendered probable, though not certain, by inductive arguments. End of chapter 14.
Sit. Okay, go ahead.
Chapter 15 of Philosophy by Bertrand Russell. This LibreVox recording is in the public domain. The nature of our knowledge of physics. In this chapter, we shall seek an answer to two questions. First, how do we know about the world dealt with in physics? Secondly, what do we know about it, assuming the truth of modern physics? First, how do we know about the physical world? We have already seen that this question cannot have a simple answer, since the basis of inference is something that happens in our own heads, and our knowledge of anything outside our own heads must be more or less precarious. For the present, I shall take it for granted that we may accept testimony with due precautions. In other words, I shall assume that what we hear when, as we believe, others are speaking to us, does in fact have meaning to the speaker, and not only to us, with a corresponding assumption as regards writing. This assumption will be examined at a later stage. For the present, I will merely emphasize that it is an assumption, and that it may possibly be false, since people seem to speak to us in dreams, and yet on waking, we become persuaded that we invented the dream. It is impossible to prove, by a demonstrative argument, that we are not always dreaming. The best we can hope is a proof that this is improbable. But for the present, let us leave this discussion on one side, and assume that the words we hear and read mean what they would if we spoke or wrote them. On this basis, we have reason to know that the worlds of different people are alike in certain respects and different in certain others. Take, for example, the audience at a theater. They all, we say, hear the same words and see the same gestures, which, moreover, are those that the actors wish them to hear and see. But those who are near the stage hear the words more loudly than those further off. They also hear them somewhat earlier, and those who sit on the right do not see quite what is seen by those who sit on the left, or in the center. These differences are of two sorts. On the one hand, some people can see something invisible to others. On the other hand, when two people, as we say, see the same thing, they see it differently, owing to the effects of perspective and of the way the light is reflected. All this is a question of physics, not of psychology. For if we place a camera in an empty seat in the theater, the perspective in the resultant photograph is intermediate between the perspectives that are seen by persons sitting on either side. Indeed, the whole matter of perspective is determined by quite simple geometrical laws. These laws show also what is common to the shapes that two people see when they see the same thing from different points of view. What is common is what is studied by projective geometry, which is concerned with what is independent of measurement in geometrical figures. All the differences in appearance due to perspective have to be learned in learning to draw. For this purpose, it is necessary to learn to see things as they really seem, and not as they seem to seem. But, it will be said, what can you mean by how things really seem and how they seem to seem? We come here upon an important fact about learning. When, in early infancy, we are learning to correlate sight and touch, we acquire the habit of reaching to a visual stimulus in a manner which is more objective than that in which a camera reacts. When we see a coin not directly in front of us, we judge it to be circular, although the camera would show it as oval, and a man would have to make it oval in a picture of a scene which contained it. We learn, therefore, to react to a visual shape in a manner corresponding to how it would appear if it were in the center of the field of vision, provided we do not immediately focus upon it, which is what we naturally do when anything visible interests us. As a matter of fact, we are constantly looking in different directions, and as a rule, only noticing what, at the moment, is in the center of our field of vision. Thus, our visual world consists rather of a synthesis of things viewed directly in succession than of things seen simultaneously while the center of the field is kept fixed. This is one reason why the rules of perspective have to be learned, although a picture which ignores them makes an impression we wrong. Another reason for the objectivity of the impressions we derive from sight is correlation with other senses, especially touch. Through this correlation, we soon get to know that a man 20 yards away is really just as big as a man 1 yard away. When children are learning to draw, they find it very difficult to make distant objects sufficiently small, because they know they are not really small. We soon learn to judge the distance of a visual object and to react to it according to the size that it would have if touched or traveled over, in the case of very large objects such as mountains. Our sense of size is not derived from sight, but from such sources as touch and locomotion. Our metrical judgments, when the stimulus is only visual, are a result of previous experience. By the time a child can speak well, he has had a great deal of this kind of experience. Consequently, our verbal reactions contain a great deal more objectivity than they would if they came at an earlier stage of infancy. The result is that a number of people can view scenes simultaneously and use exactly the same words about it. The words which we naturally use in describing what we see are those describing features which will also be evident to others in our neighborhood. We say, there is a man, not, there is a colored shape whose visual dimensions are such and such an angle vertically and such another horizontally. The inference is a physiological inference, and only subsequent reflection makes us aware that it has taken place. We can, however, become aware of it through occasional mistakes. A dot on the window pane may be mistaken for a man in a distant field. In this case, we can discover our error by opening the window, or by moving the head. In general, however, physiological inferences of this sort are correct, since they have resulted from correlations which are very common and are likely to be present on a given occasion. Consequently, our words tend to conceal what is private and peculiar in our impressions, and to make us believe that different people live in a common world to a greater extent than is in fact the case. We have been using the word objectivity in the preceding pages, and it is time to consider exactly what we mean by it. Suppose some scene, say in a theater, is simultaneously seen by a number of people and photographed by a number of cameras. The impression made upon a person or a camera is, in some respects, like that made upon other persons and cameras, in other respects different. We shall call the elements which are alike objective elements in the impression, and those which are peculiar we shall call subjective. Thus, those features of shapes which are considered in projective geometry will be objective, whereas those considered in metrical geometry, where lengths and angles are measured, cannot be made objective through sight alone, but demand the use of other senses. In the photographs, a man on the stage will be longer if the camera is near the stage than if it is far off, assuming all the cameras to be alike. But if 4 actors are standing in a row in one photograph, they will be standing in a row in another. This is an objective feature of the impression. All the differences in the visual impressions of a number of spectators with normal eyesight are exactly analogous to the differences in the photographs. So also are the likenesses. Thus, the subjectivity that we are speaking about at present is something belonging to the physical world, not to psychology. It marks the fact that the stimulus, whether to an eye or to a camera, is not exactly the same wherever the eye or the camera may be placed. There are features of the stimulus which are constant within limits, but there are others which are different from any 2 different points of view. The tendency of our perceptions is to emphasize increasingly the objective elements in an impression, unless we have some special reason, as artists have, for doing the opposite. This tendency begins before speech, is much accentuated after speech has been acquired, and is prolonged by scientific physics. The theory of relativity is only the last term, so far, in the elimination of subjective elements from impressions. But it must not be supposed that the subjective elements are any less real than the objective elements. They are only less important. They are less important because they do not point to anything beyond themselves, as the others do. We want our senses to give us information, i.e., to tell us about something more than our own momentary impression. We acquire information through our senses if we attend to the objective elements of the impression and ignore the others. But the subjective elements are just as truly part of the actual impression. This is obvious as soon as we realize that the camera is as subjective as we are. Such considerations lead irresistibly to the scientific view that when an object can be seen or photographed from a number of points of view, there is a connected set of events, light waves, traveling outward from a center. That, moreover, there are some respects in which all these events are alike, and others in which they differ from one another. We must not think of a light wave as a thing, but as a connected group of rhythmical events. The mathematical characteristics of such a group can be inferred by physics within limits, but the intrinsic character of the component events cannot be inferred. The events constituting light waves are only known through their effects upon our eyes, optic nerves, and brains, and these effects are not themselves light waves, as is obvious from the fact that nerves and brains are not transparent. Light in the physical world, therefore, must consist of events which are in some way different from the events which happen when we see. But we cannot say more than this as to the intrinsic quality of these external events. Moreover, when a number of people, as we say, see the same thing, what we have reason to believe is that light waves emanating from a certain region have reached the eyes of all these people. As to what is in the region from which the light waves come, we cannot tell. But, so the layman is tempted to argue, we can tell quite well, because we can touch objects that we see, and discover that there is something hard and solid in the place from which the light waves come. Or again, we may find that there is something there which, though not solid, is very hot, and burns us when we try to touch it. We all feel that touch gives us more evidence of reality than sight. Ghosts and rainbows can be seen, but not touched. One reason for this greater sense of reality is that our spatial relation to an object when we touch it with our fingertips is given, and therefore an object does not give such different impressions of touch to different people as it does of sight. Another reason is that there are a number of objects that can be seen but not touched, reflections, smoke, mist, etc., and that these objects are calculated to surprise the inexperienced. None of these facts, however, justify the plain man in supposing that touch makes him know real things as they are, though we are verbally forced to admit that it brings him into contact with them. We have seen on an earlier occasion how complex is the physical and physiological process leading from the object to the brain when we touch something, and we have seen that illusions of touch can be produced artificially. What we experience when we have a sensation of touch is therefore no more a revelation of the real nature of the object touched than what we experience when we look at it. As a matter of fact, if modern physics is to be believed, sight, prudently employed, gives us a more delicate knowledge concerning objects than touch can ever do. Touch, as compared with sight, is gross and massive. We can photograph the path of an individual electron. We perceive colors which indicate the changes happening in atoms. We can see faint stars, even though the energy of the light that reaches us from them is inconceivably minute. Sight may deceive the unwary more than touch, but for accurate scientific knowledge, it is incomparably superior to any of the other senses. It is chiefly through ideas derived from sight that physicists have been led to the modern conception of the atom as a center from which radiations travel. We do not know what happens in the center. The idea that there is a little hard lump there, which is the electron or proton, is an illegitimate intrusion of common sense notions derived from touch. For aught we know, the atom may consist entirely of the radiations which come out of it. It is useless to argue that radiations cannot come out of nothing. We know that they come, and that they do not become any more really intelligible by being supposed to come out of a little lump. Modern physics, therefore, reduces matter to a set of events which proceed outward from a center. If there is something further in the center itself, we cannot know about it, and it is irrelevant to physics. The events that take the place of matter in the old sense are inferred from their effects on eyes, photographic plates, and other instruments. What we know about them is not their intrinsic character, but their structure and their mathematical laws. Their structure is inferred chiefly through the maxim, same cause, same effect. It follows from this maxim that if the effects are different, the causes must be different. If, therefore, we see red and blue side by side, we are justified in inferring that in the direction where we see red, something different is happening from what is happening in the direction where we see blue. By extensions of this line of argument, we arrive at the mathematical laws of the physical world. Physics is mathematical not because we know so much about the physical world, but because we know so little. It is only its mathematical properties that we can discover. For the rest, our knowledge is negative. In places where there are no eyes or ears or brains, there are no colors or sounds, but there are events having certain characteristics which lead them to cause colors and sounds in places where there are eyes and ears and brains. We cannot find out what the world looks like from a place where there is nobody, because if we go to look, there will be somebody there. The attempt is as hopeless as trying to jump on one's own shadow. Matter, as it appears to common sense, and as it has until recently appeared in physics, must be given up. The old idea of matter was connected with the idea of substance, and this, in turn, with a view of time that the theory of relativity shows to be untenable. The old view was that there is one cosmic time, and that given any two events in any two parts of the universe, either they are simultaneous, where the first is earlier than the second, or the second earlier than the first. It was thought that the time order of the two events must be always objectively definite, although we might be unable to determine it. We now find that this is not the case. Events which can be regarded as all in one place, or all parts of the history of one piece of matter, still have a definite time order. So do events in different places. If a person situated where the second takes place can see the first before the second happens. Or, more exactly, if light can travel from the place of the one to the place of the other, so as to reach the other place before the second event. Here, we mean by a place the position of a given piece of matter. However the matter may move relatively to the other matter, it is always in the same place from its own point of view. But if light traveling from the place of the one event to the place of the other event arrives at the place of the other event after the other event has taken place, and conversely, then there is no definite objective time order of the two events, and there is no reason for regarding either as earlier than the other, nor yet for regarding the two as simultaneous. Ideally, careful observers will judge differently according to the way in which they are moving. Thus, time is not cosmic, but is to some extent individual and personal for each piece of matter. What do we mean by a piece of matter in this statement? We do not mean something that preserves a simple identity throughout its history, nor do we mean something hard and solid, nor even a hypothetical thing in itself, known only through its effects. We mean the effects themselves, only that we no longer invoke an unknowable cause for them. We find that energy in various forms spreads outwards from various centers. We find also that such centers have a certain degree of persistence, though this persistence is not absolute. The modern physicist faces cheerfully the possibility that an electron and a proton may mutually annihilate each other, and even suggests that this may be the main source of the radiant energy of the stars, because when it happens, it makes an explosion. What is asserted may be put as follows. When energy radiates from a center, we can describe the laws of its radiation conveniently by imagining something in the center, which we will call an electron or a proton according to the circumstances. And for certain purposes, it is convenient to regard this center as persisting, i.e., as not a single point in space-time, but a series of such points, separated from each other by time-like intervals. All this, however, is only a convenient way of describing what happens elsewhere, namely the radiation of energy away from the center. As to what goes on in the center itself, if anything, physics is silent. What Dr. Whitehead calls the pushiness of matter disappears altogether on this view. Matter is a convenient formula for describing what happens where it isn't. I am talking about physics, not metaphysics. When we come to metaphysics, we may be able, tentatively, to add something to this statement, but science alone can hardly add to it. Materialism as a philosophy becomes hardly tenable in view of this evaporation of matter, but those who would formerly have been materialists can still adopt a philosophy which comes to much the same thing in many respects. They can say that the type of causation dealt with in physics is fundamental, and that all events are subject to physical laws. I cannot wish, as yet, to consider how far such a view should be adopted. I am only suggesting that it must replace materialism as a view to be seriously examined.
Come on.
End of chapter 15.
Come on.
End of part 2. Chapter 16 of Philosophy by Bertrand Russell. This LibriVox recording is in the public domain. Part 3, Man from Within. Chapter 16, Self-Observation. It will be remembered that throughout Part 1, we agreed to consider only those facts about a man which can be discovered by external observation, and we postponed the question whether this excluded any genuine knowledge or not. The usual view is that we know many things which could not be known without self-observation, but the behaviorist holds that this view is mistaken. I might be inclined to agree wholly with the behaviorist, but for the considerations which were forced upon us in Part 2, when we were examining our knowledge of the physical world. We were then led to the conclusion that, assuming physics to be correct, the data for our knowledge of physics are infected with subjectivity, and it is impossible for two men to observe the same phenomenon except in a rough and approximate sense. This undermines the supposed objectivity of the behaviorist method, at least in principle. As a matter of degree, it may survive to some extent. Broadly speaking, If physics is true, and we accept a behaviorist definition of knowledge, such as that of Chapter 8, we ought, as a rule, to know more about things that happen near the brain than about things that happen far from it, and most of all, about things that happen in the brain. This seemed untrue because people thought that what happens in the brain is what the physiologist sees when he examines it. But this, according to the theory of Chapter 12, happens in the brain of the physiologist. Thus, the a priori objection to the view that we know best what happens in our brains is removed, and we are led back to self-observation as the most reliable way of obtaining knowledge. This is the thesis which is to be expanded and sustained in the present chapter. As everyone knows, the certainty of self-observation was the basis of Descartes' system, with which modern philosophy began. Descartes, being anxious to build his metaphysic only upon what was absolutely certain, set to work as a preliminary to doubt anything that he could make himself doubt. He succeeded in doubting the whole external world, since there might be a malicious demon who took pleasure in presenting deceitful appearances to him. For that matter, dreams would have supplied a sufficient argument. But he could not manage to doubt his own existence. For, said he, I am really doubting. Whatever else may be doubtful, the fact that I doubt is indubitable. And I could not doubt if I did not exist. He summed up the argument in his famous formula, I think, therefore I am. And having arrived at this certainty, he proceeded to build up the world again by successive inferences. Oddly enough, it was very like the world in which he had believed before his excursion into skepticism. It is instructive to contrast this argument with Dr. Watson's. Dr. Watson, like Descartes, is skeptical of many things which others accept without question. And, like Descartes, he believes that there are some things so certain that they can be safely used as the basis of a startling philosophy. But the things which Dr. Watson regards as certain are just those which Descartes regarded as doubtful, and the thing which Dr. Watson most vehemently rejects is just what Descartes regarded as absolutely unquestionable. Dr. Watson maintains that there is no such thing as thinking. No doubt he believes in his own existence, but not because he thinks he can think. The things that strike him as absolutely
Oh, you're loading, huh?
Alright, you got it, Simba. Yeah, you can do it. you got a problem with symbol for?
Why is the pen down?
I put treats in it.
Oh.
I'll see you on YouTube.
Oh, okay. I thought somebody had just been naughty and like knocked it down somehow without cracking it.
No, not my symbol.
You can get him.
Is that a good boy, Jet? You look like you're definitely okay. You look like you're okay. You look like you're actually feeling really good.
Mm-hmm. He's a good dog.
This is what I got.
How's that gonna work?
Well, we have to cut them in half, and then we'll staple them down.
Is that normal?
I couldn't find any designated stair runners through the store.
What store?
Menards.
I don't know if it help you.
No. So. You hate them?
You said staple them down?
Yeah.
In, I was thinking like, you were talking about like little rubber mats that just,
No, they were always going to be
stapled?
stapled or glued or caulked or. Like, they were always going to be designated down to the ground. Otherwise, there's no point in putting them on there because you don't staple them down. If you step on them just wrong, you fall down anyways. So,
You're sure on that?
yes. I would be amenable if you really hate these this much to going back together and looking at options.